All right, chemists, I am going to start this lecture, Chemistry 132b, Quantum Principles. Um, I am going to quickly recap some of the things that we have talked about, and then I'm going to introduce something new, as always, because we are entering now a pretty exciting um, part of the course, which is that we can now talk about actual atoms. So we started talking about the hydrogen atom, and in the case of the hydrogen atom, as you can see here, we found the orbital wave function, and that is a wave function. We indicate that by the letter psi, and then three quantum numbers, NL and ML. Those are the quantum numbers that completely define the orbital in which the electron sits when it's part of an atom, in this case, the hydrogen atom. And these functions are analytical in the sense that they are not bound by any approximation. They are exact solutions. So the hydrogen wave functions are exact solutions of the Schrödinger equation. We were able to solve it exactly. But we also know that the orbital part of the electron wave function is not the only part, because there's another part to the wave function, and that is the spin part to the wave function. That is indicated over here. You see here a bigger psi, capital Psi, which indicates the total wave function. And you see the first part is the little psi, that is the orbital wave function that basically describes the whereabouts of the electron. And then the second part, which is sigma now, just indicated by sigma, that is the spin state wave function. The one means that it's just one electron, okay, one electron. And that electron can have two spin states. What were those spin states? Well, one of them is alpha, the other one is beta. Okay, so alpha and beta basically correspond to spin up and spin down. That's the kind of the colloquial way of saying it, spin up, spin down. But really, these are two quantum mechanical spin states. There is no up or down really for the electron. So just please keep that in mind. We just draw little arrows up and down, but that is just for us to talk about this. But the electron really doesn't point up or down. So please keep that in mind. So the total wave function has two parts then, the orbital wave function, which has three quantum numbers, then the spin wave function, which has only one quantum number, s, which is half, okay? And so the total electron wave function has therefore four quantum numbers, NL, ML, and then the last quantum number, which is s, which is the spin state, which has two projections defined by ms. So ms is the final quantum number that defines the orbital wave function. So this is true for hydrogen, and so the hydrogen problem is kind of solved at this point. And then we started to move to a more complicated problem at the very end of Wednesday's lecture. Okay, so we moved from the hydrogen atom, which only has one electron, to the case of helium, which first of all has a more complicated nucleus, but that's the part that we conveniently forgot about. We just say, well, it's just a nucleus with a higher charge, so that's that. But then we have two electrons swarming about instead of one, and that required some new approaches, because the Schrödinger equation now, the Hamiltonian, has contributions from two electrons, right? So we talked about that last time, and what we did, very conveniently, we started to make an approximation already, and that was that we forgot or ignored the contribution from electron-electron interaction. So we basically said that electron-electron interaction part, I'm going to toss out of the Hamiltonian and then solve it. And in that case, we could solve the problem. And what we found is that the two electron orbital wave function now is a product of the two individual orbital wave functions. Each electron has a wave function, in this case indicated by psi1 for electron 1, psi2 for electron 2. These two wave functions don't have to be the same. They can be different wave functions depending on what levels these electrons sit in. Okay, so we haven't specified it what these psi1 and psi2 are. Those are hydrogenic wave functions that look like the hydrogen atom wave functions, but they could be different states for each of the atoms. Sorry, for each of the electrons. So the first electron can be in state 1s, the second electron can be in state 2p, for instance. Okay? So that is the orbital part. And the beauty of this approach is that the total orbital wave function is a simple product of the two individual wave functions. And that could be done because these two wave functions are truly independent. They don't depend on one another. Why not? Because we conveniently tossed out this electron-electron contribution, this interaction between electrons. That's what we tossed out, and that allowed us to make this kind of somewhat simple approximation such that the total wave function is simply a product of the two individual wave functions. But we have not talked about the second part of the total wave function, and that is, of course, this spin part. Okay, so whereas we have now a way of writing the orbital part of the helium atom, simply a product of two orbital states of the individual electrons, we don't have now an expression yet for the spin part, and that is a sigma part. Sigma is now 1, 2, which simply means electron 1 and electron 2. They both have spin states, and the combined spin state is called sigma. So that is what we're going to focus on right now. So let's do that. Okay, so first of all, let's go back to the case of the spin state of a single electron. And I'm going to write this in this kind of cat notation because that proves to be very important. The spin state of a single electron depends on two numbers. S is the total spin angular momentum quantum number, that is half. So that number is always half. And then ms is the projection, and ms could have two values, plus half and minus half. So what do we have then? Well, we found last time, or like a few lectures ago, two possible states, namely alpha equals half comma half, which we can call spin up. Okay, but really it isn't spin up. It's just the fact that the electron is in quantum state ms equals plus half. And then beta was the case when the electron sits in ms equals minus half. Okay, so these two states are different because they have different ms projections, different ms quantum numbers. They're not the same. These electrons have different magnetic moments because they have different spin angular momenta. So these are the two states, alpha and beta. We have seen them before, of a single electron. Now, what happens if we have two electrons? Well, each electron can be either in state alpha or state beta. Okay, so if we then have two of these guys, we can make combinations. So let's make all possible combinations. Here's one, alpha 1, alpha 2. What does that mean? Simply, it means that the first electron, electron 1, is in the alpha state, and electron 2 is also in the alpha state. So both electrons basically have the same spin state. In the case of alpha, which we typically call spin up, both electrons will have a spin up. Okay, so they have the same state and they point in the same direction, in this case, in the alpha direction. But I can also do alpha 1 and beta 2. In this case, the second electron will have a different spin state, or beta 1, alpha 2, and then a final combination I can make is beta 1, beta 2, in which case both electrons are in the spin down state. So these are the four possibilities. So basically, if I have two electrons, I have four possibilities to arrange these electrons in terms of their spin states. And it turns out that this way of writing the spin state is okay, but it's not really reflecting the actual properties of the atom very well. Okay, because what is reflecting the properties of the atom much better is not just this alpha, alpha beta, beta alpha, and so forth, but really what is the total spin angular momentum of these two electrons, because that affects the total angular momentum and affects, in turn, also the energies in some shape or form. Okay, so what we really have to look for is not so much these products of the two individual spin states, but really what is the total spin angular momentum if the electrons are in one of these states. So let's do that. We have to look not at the individual spin state, but we have to look at the combined spin angular momentum and define the quantum states accordingly. So let me show you what that means. So what it means is the following. What I'm going to do is I'm going to combine the spins of the electrons. And the way to do that, the possible combinations that are allowed are indicated by this formula. S, capital S, stands for the combined spin. Okay? Spin 1, that's S1, plus S2, that is the addition of the two spin states, or the two spin quantum numbers. Now, both of these S1 and S2 are half, okay? Because S, the total spin quantum number, S, is always 1/2, okay? So S1 plus S2 in this case is basically 1. 1/2 plus 1/2 equals 1. And then what I'm going to do is I'm going to step down in integer steps. So that means the term between parentheses says S1 plus S2 minus 1. So I'm going to basically count down in integer steps till I hit the difference between the two, S1 minus S2. The magnitude of that difference is the lowest possible combination that I can make. So what does that mean for our two electron system? Well, that means that I only have two possibilities, right? I can only have half plus half, which is 1, and then I can have minus half, which is 0. So only 1 and 0, okay? So the possible values that are allowed for capital S are 1 and 0. Those are the two ways in which I can combine the spin angular momenta. Now, each S, each capital S, has projections as always, and that is indicated now by capital MS. So for each S, there is projections that run from S to minus S in integer steps. That is true for all angular momenta, and of course is also true for combined angular momenta, as we have seen last time. So let's basically investigate this for our two electron system. Okay, so the two electrons in helium. So the first combination that I had from this way of combining angular momenta is 1. Capital S equals 1, where the two halves are adding up. All right. So in that case, the so-called multiplicity, the spin multiplicity, which is defined as 2s plus 1, gives me a value 3. What does the 3 mean? It means you have 3 projections, okay? Because ms, the projections of the total spin angular momentum, has 3 values. It runs from minus half to plus half in integer steps. So I have minus half, 0, and 1. And this is what we call a triplet state. Maybe you've heard about this, but this is really what triplet state means. It means that a total spin angular momentum, capital S, equals 1. And that means you have 3 projections, 3 possible ways. There's 3 possible ways in which you can have a total spin angular momentum of 1. And those are the projections ms, minus half, 0, and 1. The other one was s equals 0, because that was half minus half, s1 minus s2. That gave us 0. And in that case, the multiplicity is 2s plus 1 equals 1. Okay? 2s is, of course, 0 plus 1. I only have 1 left, so that's 1. And that means I only have 1 projection, which, of course, equals 0. It says minus 0, but it doesn't make any sense. It's just 0. ms equals 0. And that is called a singlet state. Okay, so I find 2 scenarios here. Okay, what I'm doing here is I'm combining the angular momenta, the spin angular momenta of 2 electrons, and following the rules here that I just laid out, I find 2 ways in which I can combine those 2 spin momenta. The first one is when I get capital S1, the total spin is now 1. In that case, 3 projections, meaning a triplet state, or I have S equals 0, in which case I have a singlet state because I only have 1 projection. Right, so those are the 2 cases. The 2 cases is I find a triplet state and I find a singlet state. What is a way to think about it? In a triplet state, as you will see, some way, somehow, the 2 spins are kind of helping one another. Okay, so they're kind of going up both or down both. So that is the case of S equals 1. And in the singlet state, the 2 spin states are kind of counteracting one another. Okay, that's kind of like a physical way to think about it. So that you get S equals 0. The 2 spin states cancel each other out. It gets total spin 0. So let's now combine these 2 things and basically give these spin states names. Okay, so my combined spin state with 2 electrons is now defined by the 2 quantum numbers capital S and capital MS. Okay, those are the 2 quantum numbers that fully define my so-called combined spin state. And the combined spin state is really the spin state that I have to consider. Okay, so we found again S equals 1, and the combinations then are 1, 1, capital S equals 1, projection equals also 1. Okay, and then of course capital S equals 1 again, but then the projection is 0 or the projection is -1. So I find 3 possibilities, 3 possible states. Okay, so these cats indicate the states in which these 2 electrons combined can sit in terms of their spins. Now the last possibility is S equals 0, and I found in that case 0, 0, because total S equals 0, and the projection is also 0. So I have 4 possible spin states. 4 possible spin states. Now remember, previously I also found 4 spin states. The alpha is alpha, beta alpha, alpha beta, and beta beta. So those are 4 possibilities. I still have 4 possibilities. I haven't created or destroyed any possible spin states, but I have written them in a very different way, namely in terms of their combined spin. And this is the quantity that is useful for understanding the properties of the atom, an atom like helium. So let's give these states names, okay? So I'm going to call the first one sigma. Sigma is always the spin state, and then it has a superscript 1, okay, and it says plus. That's the subscript. The 1 is the projection. The total projection is 1, and the plus indicates here that it is actually the triplet state. Okay, so the second one is sigma 0 plus, and the last one is sigma -1 plus. So the superscripts indicate the MS value, and the plus basically indicates that I have combined the 2 spin states of the 2 electrons, and they kind of add up. They don't really counteract, they kind of help one another. And the last one I simply call sigma minus, because here the 2 spin states don't help one another. They seem to be counteracting one another, and therefore I put a minus sign there. So these are the new names that I'm going to give to the combined spin states. They're all called sigmas, and then the superscripts and the subscripts, they tell me which particular one I'm talking about. Now, how do these combined spin states relate to the previous way in which we wrote the spin states? Well, it turns out we can make that connection. Okay, so the first one is when the 2 spins of the 2 individual atoms, 2 individual electrons, are both in the same direction, alpha, alpha. Okay, in that case, they're definitely helping one another. And you can see the projection now is 1. So clearly, they point in the same direction. They're both going up, right? The second one is a little funny looking, because it turns out you have to make a combination. Combination of 2 of these spin states, alpha 1, beta 1 plus beta 1, alpha 1, beta 1, alpha 2, and then it has a normalization factor, 1 over square root of 2. That spin state, that combined spin state, has the exact properties of the spin state that is indicated by 1, 0. S equals 1, MS equals 0. So that is sigma 0 plus. Sigma 0 plus is a linear combination of these spin states, okay, written in terms of alpha and beta. And then finally, the last one that has a total spin of 1, but has a projection of -1. The -1, in this case, means that the 2 spin momenta are pointing in the same direction, right? So this is beta 1, beta 2. So the 2 electrons are both in the spin down state. You can see here the first one and the third one are kind of easy to understand. The middle one is a little bit more difficult to understand. Okay, and the reason is that truly this is a combined angular momentum. It's not individual momenta, it's really the combined state that defines the properties. Okay, the final one then, how do we write that? Well, that is kind of analogous to option number 2, but now the plus sign is a negative sign. Okay, so this is also a combined spin state, a superposition of two possible states that are combined in a certain way such that the combined angular momentum has the properties S equals 0, ms equals 0. Okay, so these are the four spin states that the two electrons can be in. There are no more possibilities. This is it. So we have two ways of writing it. One is the situation on the right-hand side, which is the old alphas and betas. And then on the left-hand side is a new way of writing it in terms of truly combined spin quantum numbers, capital S and ms, which turn out to be the defining quantum numbers that help us understand the properties of the helium atom. Okay, so now then we have to come full circle because we talked about the spin states. We also have the orbital states. And previously we saw that the orbital states can indeed be written as simply the product of the two individual orbital states, psi1 and psi2. So now we're going to combine then the spin states with the orbital states. And we're going to do this by realizing that in the ground state of helium, the two electrons are in the same orbital, okay? So they both are in the same orbital. Psi1 and psi2 are basically 1s orbitals. So that is going to be important on the following slide. So what kind of combinations can I make then? Well, the orbital state is pretty much given, okay? Psi1 and psi2 are both 1s wave functions. Done. There are no other combinations I can make. The only combination I can make is 1s for particle 1, 1s for particle 2, and that's it. There are no more possibilities. So that's easy. The orbital state of the two electrons is only one state. But for the spin state, I had four possibilities, as we just talked about above. Okay, so what we have then is psi1, psi2 times each of these spin states, giving me four possibilities. Okay, so there are four possibilities for the total wave function of these two electrons in ground state helium. Okay, the question now is, that's weird. How can there be four states? I mean, isn't there supposed to be just one state in a ground state, or maybe two, or I don't know. What is it? How can it be in four states? Maybe some of them are not valid. So let's investigate that. Let's see which ones of these is the actual kind of unique description of the ground state of helium. In order to do that, we need some new information. Okay, and this information is something that you are already familiar with, but maybe you didn't realize that it came from this direction. And that is Pauli's principle. Pauli's principle is typically translated as you cannot put more than two electrons in a single orbital. Okay, that's what people typically understand it to mean, but that's not what Pauli's principle states. Pauli's principle is based on a very fundamental quantum mechanical property, and that's written over here. We haven't talked about it, but it's a very important foundation of quantum mechanics, and that's the following. The wave function of a fermion, which is what an electron is, must be antisymmetric, and that means, what does it mean, antisymmetric? It means that the wave function must change sign upon particle interchange. All right, that sounds very cryptic, so let's make that more explicit. Here's the wave function, okay? Capital psi 1, 2 means, particle 1, it's electron number 1, and electron number 2. So there's two electrons in this state, this total capital psi state. And I can specify there's an orbital part, psi1 and psi2, and then there's a spin state, sigma 1, 2. Okay, so the two electrons, they have orbital states and spin states, and the spin states now I indicate with sigma 1, 2. Now, what does particle interchange mean? It simply means that I'm switching the kind of occupation of the particle. So the first orbital wave function, psi1, is now going to be psi2. And the second wave function is going to be psi1. And the same for the sigma. I'm going to swap the positions of the particles. Particle 1, electron 1 becomes electron 2, and electron 2 becomes electron 1. So basically, I get this. Capital psi 2, 1, I switched the location, so the occupation of the wave functions are now different particles. I switched their location. Okay, so the first orbital wave function accommodates now particle 2. And the second orbital wave function has now particle 1 in it, right? And the same for the spin states. So I switch the positions of the particle also in terms of the spin state. That is what particle interchange means. So what Pauli says then, he says, if you do that, if you do the particle interchange, then for this wave function to be a valid wave function for a fermion, which is what electrons are, the sign of the wave function must change. And if it doesn't change, it's not a valid wave function. Okay, so that's a pretty dramatic statement. It basically says a lot of wave functions that you may encounter that you can make by making combinations of possibilities, a lot of them may not be valid because they do not have this property of anti-symmetry, meaning the wave function changes sign upon particle interchange. Okay, so let's do that. We can do this. You'll see. It looks very cryptic, but it turns out it's really not that complicated. So here's the first combination I have. I take the first one, the orbital state, and I'm going to swap the position. So I get sigma 2, sorry, not sigma, that's psi 2, psi 1. Okay, that is the first part of the wave function. I'm talking about this part where I swap the position. So particle 2 is first, right there, and then particle 1. Okay, so that means on the orbital side of things, I have interchanged the particles, and I'm going to do the same thing for my first possibility for the spin state, which is sigma 1 plus. I'm going to swap the particles. Okay, so what I'm getting then, if I write this out explicitly, I get the following. Because these two orbital states are the same, they're both 1s. Since they're both 1s, they're identical. So if particle 2 sits in the first one and particle 1 sits in the second one, it doesn't matter. You can just swap them back and forth. I can write it as follows. Okay, I can simply say the position, which one I write first, doesn't matter in this case, because those two psi's are the same orbital state. So there's no difference. So the order, therefore, doesn't matter. And the same is true for the spin state, which is what this sigma is. Sigma 1 plus equals alpha alpha. And in this case, alpha 2, alpha 1. So first particle 2, then particle 1. But because these two states are the exact same quantum mechanical state, it doesn't matter which one I write first. In other words, I can just write it as follows: psi 1, psi 2, and then sigma 1 plus, where the order is reversed, 1, 2, because it doesn't change anything. Okay, so this wave function, if I do particle interchange, is not changing its sign. So according to Pauli, this is not correct. This is not a valid wave function, and therefore this cannot be the ground state of the helium atom. What about the second one? The second one was a possibility of sigma 0 plus. Okay, the orbital part is the exact same as above. It hasn't changed. Okay, so the orbital part is the exact same as above. So I don't have to focus on this. I can only focus on the second part, which is the spin part. I'm going to swap the particles. So 2, 1. I'm going to write this whole thing out. Okay, which is alpha 2, beta 1 plus beta 2, alpha 1. Okay, so but what I can do now, I can actually turn this around. Okay, I can write this in such a way that I get the exact same spin state again. All right, so the spin state hasn't changed in the case of sigma 0 plus. Once again, this is the exact same as if you swap the particles, because this is combination 1, this is combination number 2, and if you swap the positions, it doesn't matter, you get the same. Okay, so again, sigma 0 plus is also invariant upon particle interchange. All right, so in any case, this is the last possibility where I have a sigma plus, that is the combination -1. In that case, I had 2 betas. All right, if I swap the betas, and because these two wave functions are the exact same, so the spin states are the same, I can change their order at will, and I basically get the same function back for the spin state. All right, so in any case, what I'm getting is the same function again. So all these 3 possibilities, as you can see, will not change their sign if you do particle interchange. So there's only one possibility left. Hopefully this will work. all right? And it will, as you will see, okay? The orbital part hasn't changed, still the same thing. So I use the same kind of logic here. I can swap these things back and forth at will. But now the sigma minus state has very different properties, because instead of a plus, there's now a negative sign. So now it actually doesn't matter what the order of these two terms is, because if you swap it around, then this negative sign is going to be in a different location. Okay, and then you can take it out of this parentheses, and that's exactly what happens. So if you try to write the original wave function in terms of the new one, you can only do that when the negative sign is taken out of these parentheses. Okay, so basically you get the same wave function back, but there's a negative sign now. Okay, so the only wave function, the only spin state that has this antisymmetric property upon particle interchange is this guy. Okay, sigma minus. Sigma minus is the only spin state that has this property. You can verify this for yourself. If this goes too fast, just look at it. Just fill it out and try to rewrite it in terms of the original. And you will see you can only do that when you pull this negative sign out of it. Okay? So what we have then, only one possibility. This is the only antisymmetric wave function, the only valid one. And therefore, if two electrons occupy the same orbital, then you must have this final spin state. Okay? Sigma minus, which is the one when s equals 0. When s equals 0, the two spins are counteracting, therefore they are anti-parallel. Right? They're anti-parallel. But just to kind of underline this is the spin state. Okay? That is the spin state. But the spin state is not this guy. So typically when we think about spin down or spin up or anti-parallel, we think about what does it mean? Is it beta beta, alpha beta, or alpha alpha? No, it is this combination. It's this linear combination. That is the one that has the right properties. So it's not just simply taking alpha 1 and beta 2. It's about taking a specific combination of alpha and beta. That is the one that has the right properties. And this, therefore, is the correct spin state of the two electrons in the helium atom. Okay, so let's now write this whole thing out. The one S2 state, that is the ground state of helium, has S equals 0 and MS equals 0. That must be the case. Otherwise, it doesn't comply with Pauli's principle. And to make a long story short, it's the old rule that we already know. Okay, simply saying no two electrons can occupy the same orbital. But this is the real reason why that is so. It's not an arbitrary statement. It's actually very deep physics that governs this principle. Okay, so the last thing I'd like to point out now is to basically expand this, not just to spin, but also to the other two angular momenta, which is the orbital angular momentum and the total angular momentum. That means the combination of spin and orbit angular momentum. So the total orbital momentum, and this is relevant because we have two particles now. Okay, so L, capital L, now depends not only on the little l of one electron, but there's two electrons. Two electrons are both in a particular state. This state will have a particular L quantum number, and so each electron contributes that L quantum number to the total. The ways in which you can combine these two orbital angular momenta, little L1 and little L2, is the exact same rule as before. And it's called the so-called Clebsch-Gordon series. Clebsch-Gordon series is a combination of angular momenta of two particles. You add them up, you step down in integer steps, okay? And then till you hit the bottom, which means the difference between the two. The magnitude of the difference is the lowest possible combination that you can make. The same is true for spin. Okay, so they follow the same rules. These are the valid ways in which you can combine two angular momenta. Okay, in this case, the top line here for orbital angular momentum, the second line, which we just saw, for spin angular momentum. These are the valid ways to combine it. And then for the total angular momentum, what we do is we are adding up capital L and capital S, following the same rule. Okay, so that is the way to determine the total angular momentum. Why do we have to do this? we have to do this because now we have two particles, two electrons instead of one, and therefore the total, the way they combine their angular momenta is what defines the properties of the atom. This is the way to do it. And it seems like this is a set of rules, and it seems confusing because there's a lot of letters here, okay? But in the end, it's simply, the rules are not really that difficult. It's just adding things up and stepping down and making combinations, okay? So in principle, everybody can do this if you kind of commit yourself to read through this several times and follow the rules. It's really not that difficult. So let's do that now for helium, okay? So what we're going to do is we're going to write down the so-called term symbol for helium. Previously, we wrote down the term symbols for hydrogen. Remember that? But there was only one electron in hydrogen. Now we have two electrons in helium, and so we have to compute and determine the total momenta in the correct way. All right, so let's do that. You'll see that it's actually not that dramatic. So for ground state helium, I have two electrons. Both electrons are in which state? The 1s. The 1s state has little l, 0, always. Okay, that's the definition of an s state. So there you go. L1 equals 0 and L2 is also 0. If that is true, then the total orbital momentum, capital L, is also 0 because both are 0. Okay, so capital L equals 0. Done. The spin angular momentum, we know, we just focused on it. Okay, S1, S2 is half. I have two combinations, 1 and 0. That's the one we just learned about. And we also learned about the fact that in the ground state for helium, only S equals 0 is the correct solution. Why? Because that is the only one that produces an antisymmetric wave function, according to Pauli. That is the only one we can choose. So that is the next step. So L equals 0. S is also 0. What about J? Well, J is L plus S. And, if both are 0, that means J is also 0. Okay? So what I'm getting then for the term symbol is the following. I get multiplicity, which is spin multiplicity. If capital S equals 0, that means that 2s plus 1 equals 1. So that's what the 1 means. That is a superscript 1. Then I get a capital S. That is the total momentum from the orbital. Okay, so that is basically this guy. It is 0, and 0 always corresponds to an S. Remember that? So for the orbital state is an S right there. And then the J number, which is the number right there, is 0 as well. Okay, so I get spin multiplicity is 1. That's 2s plus 1. Capital S is the capital L number here, which corresponds to a spin orbital, sorry, not spin, an orbital angular momentum of 0, which corresponds to S. This is the capital version of an S orbital. That's the S. And then the 0 here is the capital J number, which is also 0. All right, so I think the confusion here sometimes is that there's a lot of S's and L's, and it just gets a little messy sometimes. But just if you do your bookkeeping right, it's actually just applying a bunch of rules, which is just adding and subtracting in the right way, and that's it. So no higher order math, just a little bit of bookkeeping that will allow you to determine the term symbol of the atoms that are relevant to us. So ground state helium term symbol is 1s0. Okay, and we'll see what that means and how we can deal with this, because it turns out these term symbols are defining the spectroscopy, the spectroscopic transitions in not only hydrogen, but also in every other atom. Okay. All right. So before we close, I'd like to bring up the following point, which is very, very important, and that is this effect of electron-electron repulsion. Remember, we have tossed out this effect for convenience sake. Okay, but of course, we know that that is not correct. So we need to bring it back in some way or form. We did it last time through the so-called J integral, but we are here doing it in a kind of another quasi-approximative description. All right, so the trick really is how to kind of deal with this VEE term in the Hamiltonian, okay, because it depended on the distances between the electrons. Okay, so if I have electron number 1, then I have to sum over all the other electrons. What I'm going to do is I'm going to determine the distance between electron 1 and every other electron, I, in the atom, okay? And then I have to sum over all these interactions, all these Coulombic interactions. Now what we can do is, and this is very approximate, is the following. What I'm going to do is I'm going to say, well, I'm going to only consider R1, which is the distance from between the electron and the nucleus. That's R1. So this, I'm considering only one electron. And then I'm having a sigma here, which basically accounts for all the accumulated effects of all the other electrons in the atom that basically reduce the effective charge of the nucleus. So that's what I'm doing. I'm going to take this whole sum. I'm going to take all the effects of all the other electrons, clump them together, and say, well, the total effect of these other electrons is that they effectively reduce the charge of the nucleus. So the effective charge of the nucleus is changed because other electrons with negative charges are in the way. Okay, so this sigma here has nothing to do with spin state. The sigma here is a so-called shielding constant. The shielding constant is different for different atoms and for different electrons in different atoms. Okay, so this is a specific number, but you can determine this empirically, and it's a convenient way to describe the effects of electron-electron repulsion. So what I'm going to do then is, since this sigma is an effective charge, so a shielding constant, what we have is that the effective charge of the nucleus is the original charge minus this so-called shielding effect. The shielding effect is the effect of all the electrons swarming about in the atom and therefore effectively lowering the charge of the plus charged nucleus. Okay. So the effective charge, therefore, that an electron sees is the total charge of the nucleus minus the so-called shielding factor that is there because other electrons are in the way and block the view of the nucleus that this particular electron has. Okay, so that's the nucleus screening constant, sigma. So what is one way to think about this? I like this picture a lot because it actually indicates what the electron experiences when it's part of an atom. So consider now an atom that has many electrons, okay? And consider now that the rock band that is playing there is basically the nucleus, all right? The nucleus is an exciting place. In this case, you are an electron, you'd like to see the band play, okay? But you can't because there's all these other electrons in the way. And so they're literally blocking your view, and therefore the pull of attraction that you have towards the nucleus is a little bit less because the other people are in the way. Okay, so the attraction is the strongest between you and the band if you stand up front. You can make eye contact with the singer, you know, and you can see the drummer sweating. That is great, right? That's exactly what you want. It's a great attraction between you and the band. But if you're farther away, that attraction is a lot less. So that's the same analogy that the electron has when it sits far away from the nucleus, and the interaction is screened by other electrons that are in the way. So that leads to some changes that are going to be important, okay? So it turns out that if you are able to find your way through the crowd and get all the way up front, that you benefit the most from the attraction of the band players, okay? It is the only way to make direct contact with the band players. As soon as you're farther away, then that contact is going to be reduced. So we have to look at the orbital wave functions of the different states and see which of the wave functions can sneak the closest to the band. All right. So that is what we see here. See here different wave functions in the n equals 3 state. Okay, the principal quantum number is 3. I have 3 possibilities, S, P, and D. And here are the radial distribution functions. We know what they are now. So this is what we calculate from the radial distribution function. And we see here that this S function is sneaking very close to the band, okay? And so therefore they can, this electron that sits in this state can benefit enormously from this attractive force that is between the nucleus and the electron. For the P, it's a little farther out. Now this peak is higher, so you may argue, well, this is higher, so therefore it can maybe overwhelm this little tiny peak over here, but that's not true. There's a disproportional effect of being close. Okay, so that's the same as if you are standing in front of the rock concert. You really want to be in the front row, otherwise, it's not going to happen. Okay, so you have to be on the front row. Even in the second row, it's already reduced by a lot. Okay, so it doesn't help if this peak is higher. Same is true for D. Very strong peak here, but too far away to have this very beneficial effect of attraction. Now, why is this important? Every time you have very strong interaction between the electron and the nucleus, that leads to a favorable interaction. That means lowering of the energy. Okay, the electron benefits from the interaction by lowering its energy. So that means that the S electron has a lower energy effectively than the 3p. Okay, because the 3p doesn't have this additional attractive interaction with the nucleus. Therefore, this favorable energy lowering effect is not applicable to 3p as it is to 3s. Okay, so basically what we saw now in hydrogen, that these wave functions all have the same energy. Why? Because there's only one electron and there is no shielding. Okay, but in the case of the the helium atom, I have the shielding effect being very real, and that means that there is now an advantage to being close to the nucleus because you are not shielded by other electrons, right? So as soon as you have more than one, so that's helium, as soon as you have more than one, this shielding effect is going to be a dominant effect that is going to favor electrons that can sneak up very close. All right, so this effect is not relevant in hydrogen, but it is relevant in helium, and therefore the difference between helium and hydrogen is quite dramatic, because this energy levels being all degenerate in n equals 3 is now being lifted. Okay, and the same effect is happening for the difference between now. This is an n equals 4 state, which is the 4s. This is n equals 4, and of course this is n equals 3. Okay. N equals 3 is a lower principal quantum number, n equals 4 is higher, but the problem here is that the 4s is getting closer to the nucleus than the 3d can, and therefore benefits disproportionately from this attractive interaction between the electron and the nucleus. And therefore the 4s has a lower energy than the 3d. Okay, so this is again the same kind of reasoning, but now in between states or levels with different principal quantum numbers n. And this is the reason why, we have this lifting of the degeneracy that characterize the energies of the orbital states in hydrogen. In helium and any other polyelectronic atom, we have this degeneracy lifted. Okay, and we see here indeed the 2s and the 2p are at different levels. The 2s benefits more from this interaction, therefore is lower. The 2p a little bit less, and therefore has a higher energy. Same is true for the 3s, the 3p, and the 3d, as we have seen, and between states of different principal quantum number n, in this case, the 4s and the 3d. The 4s and the 3d are very close in energy, and there's very subtle effects, as we will see, that actually are going to play a role to and that actually drive the exact electron configuration of atoms that occupy these states. Okay, so we'll see some interesting exceptions and so forth, but the basic principle that drives the differences is this shielding and penetration effect. Okay. All right, so that's it for today. We'll continue on Monday, and we'll see what happens to helium. There's much more to say about the helium atom, it turns out. So we'll have to look at the orbital quantum state a little bit better next time. Okay, folks, let me know if you have any questions. If not, I'll see you again on Monday.